We are a little pressed with the time, so I would like to go ahead with the next presentation. Thanks a lot.
Okay, thank you.
So moving on to the next presentation, this is from SCHMID. Dr. Christian Buchner, who is a Vice President of Business Unit for PV at SCHMID, is going to talk about innovations in wet chemical solutions for the state-of-the-art and advanced cell architectures. Christian, the floor is yours.
Shaban, thank you very much. I hope you can see my screen now.
Not yet, but I think it's coming up.
It.
Yeah. Oh, no.
I'll do it again.
Yeah.
Very good. So first of all, thank you very much for inviting me. Thanks to all the team, Michael and Santoshi and Shaban, to preparing this great conference again. I'm very pleased to be part of it and hope I can contribute with my presentation. Yeah, so today I will talk focus on wet chemical solutions for the state-of-the-art advanced cell manufacturing. Basically, would like to just go a bit more global first with SCHMID. So we're 155 plus years family-owned company, 800 staff today, very heavily patent-driven, and of course do a lot of research with 150 scientists, developers, and engineers on our research center here in Germany. We do produce actually our equipment in Germany and in China. And we also do joint venture business in South Korea, Turkey, and Saudi Arabia. Well, going back a bit in the PV history, we actually started pretty early on, 2002, where we delivered the first fully automatic module manufacturing lines for solar world. And this was basically our entry into the photovoltaic industry. So we came out of the printed circuit board industry, inline processing tools. So we thought this is a very good thing to do and replace batch systems in wafer manufacturing for acidic texturing. So we started with the early movers here in Germany, like QCell Schott and the solar world, and did grow with them beginning from 2004 with wet processes. Then 2005, we started introducing further wet process system, which is the horizontal single site wet chemical junction isolation system to replace the plasma edge isolation and laser edge isolation that was briefly also introduced into the industry at that time. And then we moved ahead and strategically decided to go ahead with the PV industry and started also our first turnkey projects actually in India with I think everybody knows Musaber and Indosolar. And also we shipped our first APCVD systems to high volume manufacturing for IBC production. So we then also moved out of the European PV growth into China. China 2008-9 started also tremendous growth in the PV industry, and well, we started with 1,100 wafers per hour throughput at that time, and people advanced to higher throughputs, as you could see also today from all the presentations where we are right now. So we introduced our 10-lane systems with a throughput at that time, achieving about 8,000 wafers per hour already on, of course, at that time, M2, M4 wafer sizes. And we shipped 50 gigawatt actually at that time within the 3 years, basically to manufacturers all over the world, but predominantly, of course, to China. And then, of course, as we could see already on the horizon, the move from multi to mono wafers, we introduced our single-site alkaline texturing system and as well as the selective emitter. that enhanced the back edge electron emitter, which enhanced the efficiency at that time. And then following year ramped up our first production lines on PERC, supported by SCHMID wet processes. Then 17, in continuation with the mono trends, we also introduced the horizontal alkaline polishing with a mono, of course, that could drive out the NOx gases out of the manufacturing, and was, of course, a very logical thing to do. And of course, with all the 10-lane success we have had in the past years, we also introduced now our 10-lane tools, which are ready for TOPCon manufacturing, M12 wafer size, for all the processes required for the TOPCon manufacturing, but also other manufacturing to come, texturing, polishing, poly wraparound, and glass removal. Yeah, this is how the system looks like. Basically, you have a system that's accessible from both sides. You have a catwalk that separates the main process system from the chemistry cabinet and pump rooms. We have it, of course, as a single-side etching, but also immersion processes, acidic, predominantly, of course, for HF etching, and alkaline processes for texturing and polishing. So, as I said before, it's NOx-free, so goes up to now 10,000 wafers per hour at very high uptime, as our customers are using it from our systems. It is ready for M12 or even larger. So we have had customers, they even send us, of course, larger wafers, and we can generate also process wafers with thickness down to 50 micron. That has been also proven in our lab here. All the material used in the systems is PP or PVC, PVD-F material, so no metal, of course. The process chambers are modular and adjustable to the process needs for future cell concepts. Like I said, single side immersion. Optionally, we can do a CDA bubbling or ultrasonic inclusion into the systems. And we have different tool configurations available for polishing, oxide removal, wraparound removal for all doped glasses, polysilicon, PSG, BSG etch, and also the systems are able to generate a wet tunnel oxide using an ozone generator for thin ozone layer generations. Very important for us, as I explained in my introduction, that we early on replaced batch systems are currently dominating, but we are really on the quest and convinced that the inline solution is, for several reasons, a superior solutions. The wafers run gently through the system, as you can see on the transport layer here, from bath to bath, versus stacking the wafers into a cassette that is moved around. The wafers are touched on the edges and harmed. You have shadowing that is created by the carrier, and also due to the process, the larger the wafers get, the thinner the wafers are getting. The risk for a wafer sticking together in the process is definitely there. Also on the breakage side, we can discuss and argue probably hours on what is the particular breakages on the particular tools, automation and process systems. So I've just sketched it here with an X. So basically, if you compare a batch polishing today, as it is today, you have the inline oxide removal, where you have three systems that add to the breakage with a certain percentage. Then you have the automation with the process system again 3 times. So you add up 6 times X versus with an inline polishing where you only have 3 times X. So basically you have 2 times less breakage as in comparison to the batch system. Coming to our systems, we offer alkaline texturing. It's an inline system. It's a single site process. We have proven that the system can fully work inline, so leave the rear side even unsaw damage etched. So basically, you have a pre-clean and alkaline texturing with basically it's a KOH bath at elevated temperatures. You do then, of course, rinse with clean. Metal clean and ozone clean, rinsing and drying That is a patented process we have. It's a rain box type of system. So basically the hot chemistry is applied through a rain box on the surface of the wafers, and every rain box in a row is replacing the surface again with fresh chemistry to support very nice, very tiny textured pyramid structures. It's a single site process, later perfect condition for polishing. Very important, it does use about 30% less water consumption as a batch system. Like I said, KOH water additive at the temperatures between 60 and 80 degrees, depending on the additive. We remove 4 to 5 micron typically on each side. I'm sorry, on the single side. Reflection is below 12%, and the range typically we have in the industry for this reflection at 600 nanometers is smaller than 9%. We have a very homogeneous chemistry flow to the wafer that supports a great uniformity, wafer to wafer, not only within wafer, but wafer to wafer uniformity. And with this, of course, we have no shadowing like you would have in a cassette, and as I pointed out earlier on, less breakage. Then we have the alkaline edge isolation system in our portfolio, where you start with an inline single site oxide removal to access the rear side for polishing. Then you do a bath with KOH, again, elevated temperatures for the rear side polishing. Then you do rinse and surface clean. Then you can do a rinse and dope glass removal, or you just leave the glass on. That depends on your process. The same system, very similarly, works also, of course, for the poly wraparound and BSG removal, or dope glass removal, I should say. You do again a preconditioning. You do a poly wraparound removal, single-sided, rinse clean, dope glass removal. Then, depending on the process, again, you're using a rinse and dry. So this system is using a patented water masking, which we have worldwide as a patent. It is suited for ultra-thin wafers. It's a full, again, also texturing PVDF and PVC, PP design with a sophisticated thermal expansion management and a new transportation system, which we have invented to provide a perfect, perfectly cleaned surface. Also very important for us to mention is that depending on what kind of system and doping you use in your polysilicon process, you may have to use a different process recipe slightly. We've run through our systems all sorts of different combinations done with the APCVD, LPCVD, PECVD systems. And we found that most of the dope glasses or polysilicon stacks we can remove. What we've seen is very difficult is a PECVD P+ poly, which is very difficult to etch. Yeah, coming to the TOPCon, which is a major topic of this conference, and we also see aligned with the other speakers prior to my presentation that typically you do see two process routes. One is the LPCVD driven, which is historically was the first one that came into mass manufacturing, is still dominating, but slowly replaced by the PECVD process shown on the right side. Main difference here, we do see that it differs with the LPCVD is done typically on ex situ doping versus the PECVD that is using the in situ doping process flow. But as you can see with the green boxes here, we do support both processes with our SCHMID wet tools. Yeah, so there's a large variety of different cell concepts, of course, on the TOPCon options out there. But recently we do see, of course, also new trends where already people are looking beyond TOPCon on a standard cell structures. So what's basically next is a top core. Is it a hybrid IBC heterojunction? I think also that can be argued in length. We see that we can support all these technologies with our wet tools. Our wet tools can be, of course, modularly designed to serve all the new cell architectures. So that brings me basically to the conclusion of my talk. The SCHMID wet process solutions are meeting today the state-of-the-art requirements towards the processes for the current cell manufacturing, but also for future cell architectures. The system can handle, of course, M12 or even larger wafers, and with much room for decreasing wafer thickness as the industry moves on. And due to its water and chemistry management, the system has the lowest cost of ownership in the industry. That is basically because of the consumption of chemistry, especially consumption of water, but also breakage reduction in comparison to others. So that's basically my contribution to the conference. Thank you very much for your attention, and I'm open for questions.
Great. Thank you, Christian. It was very nice and very brief presentation. So I have one question from my end. So since you are also supporting the heterojunction, you know, how difficult or how critical is the cleaning regime when it comes to the TOPCon or heterojunction? So do you see some difference there in terms of cleaning regime?
Well, actually cleaning, I think that's a very good point, Shravan. Cleaning is more and more crucial as we go to higher efficiency. So that is really something that is, I think, of course, extreme. Heterojunction surfaces are extremely sensitive to contamination. So here cleanliness is even more important than for TOPCon. But I would also claim that cleanliness for TOPCon is definitely very important and plays a major role in future efficiency increases. So this is clear, and this is actually what we have also taken care in our systems, so that we have also reduced the particles down to zero. The special transport systems we have developed to not contaminate the system. And of course, also the cleaning in the system, which involves ozone cleaning, of course, that also contribute to cleaner surfaces.
Okay, if you allow me, I would like to ask you one more question again regarding heterojunction, because you covered a lot on TOPCon. So I just want to reflect a little bit on heterojunction side also. Mm-hmm. So, you know, previously it was more or less like there were two major methods, RCA and ozone. And what I heard recently is most of the people are, I mean, the industry is moving towards ozone-based cleaning mechanism. So what's your take on this, these two cleaning methods, which are very crucial for heterojunction?
Yes, I agree. So I think with the ozone cleaning, we're definitely meeting the requirements for heterojunction, for the cleanliness for the surfaces. But well, we try to stay modular, and we have no problem to also include RCA cleaning into our system. So we have done both already and realized so both options are available. But my personal opinion is that ozone cleaning will well be sufficient to do sufficient cleaned surfaces for heterojunction.
Okay, I think there is also one more question in the chat box. So, you know, in how far does a reduction in breakage at the wet chemistry have an impact on the overall breakage? So I think it's more or less like how much is the wet chemical contribution, wet benches contribution to the overall mechanical yield?
So I think very difficult. So typically our breakage in the system is smaller than 0.05%. So that's what we have proven in industry, in mass manufacturing. So basically you have 3 wet tools in TOPCon manufacturing. So you if you would add up, then you have less than 0.15% breakage that is contributed by the wet process to the overall process. And I would claim with the SCHMID tools, you would probably even end up at around 0.1% for all wet processes.
Okay. And here also there is one more tricky question. So do the weak wafers that survive the inline process break at a later stage?
No, actually, the funny thing is we've seen that there is a region in the wafer thickness that is around 140 micron, 30 micron, where the wafers are even more brittle than they are below 100 micron. So I would claim that the very thin wafers are pretty flexible and do not break later. If you don't impose processes that would break them, of course. But I would claim that the breakage added throughout the process to thinner wafers is less than let's say for wafers that are around 140, 130 microns.
Okay, great. So thanks a lot for this very nice overview and also answering the questions. And please stay back, and if there are any questions, please respond in the chat box. And of course, we will again talk at the end. Thanks
again,
a lot,
thanks to everyone for listening, and yeah, look forward to the next conference. Thank you, and for the panel discussion. Thank you.